CEF and TREF are highly reproducible, as shown in this 5-time replica analysis of a dual-reactor LLDPE resin performed with a fast analytical method. The analysis time per sample is 90 minutes. In addition to polymer concentration, the infrared detector provides the content of branches per 1,000 carbons by the distinct absorbance of the CH3 groups, which in PE copolymers follows a linear dependence with dissolution temperature as expected. The integration of a viscometer also provides molar mass composition dependence. This dual reactor resin shows a peak at 70 degrees Celsius with higher molar mass. Dissolution temperatures in TREF do not always follow the same trend as the crystallization temperatures in DC or Christoph. This becomes evident in the analysis of a blend of both P and PP. Polypropylene elutes or dissolves at a higher temperature in TREF than polyethylene, whereas in DC or Christoph, polypropylene, with a larger undercooling than polyethylene, crystallizes at a lower temperature than PE, so they cannot be fully separated by DC or Christoph. On the other hand, the presence of ethylene in EP copolymers results in a shift towards lower temperatures in both TREF and DC or Christoph. This EP resin will not separate from PE in TREF, whereas in DC or Christoph, it will have a baseline separation. Choosing the right technique is highly important when dealing with complex industrial resins containing both PE and PP fractions. An advantage of using an infrared detector in these analyses is the simultaneous measurement of methyl content per 1,000 carbons together with the overall concentration, which unequivocally identifies both PE and PP resins as shown by the yellow lines indicating the level of methyls per 1,000 carbons. The TREF analysis of a high-impact PP copolymer is a good example. The peak at 115 degrees Celsius corresponds to isotactic PP homopolymer with 333 methyls per 1,000 carbons. At around 95 degrees Celsius, the methyl content goes down as we approach a small PE peak at 93 degrees, still showing a significant methyl content around because it co-elutes with lower tacticity or lower molar mass PP fraction. The material eluted between 95 and 40 degrees corresponds to a small content of LLDPE resin produced in the second reactor when the large rubber fraction is produced, which elutes in the end as a soluble fraction. It is interesting to see the linear dependence of methyl content with temperature in the LLDPE fraction range. Thus far, we have discussed the importance of the short-chain branching distribution and the analytical crystallization techniques, TREF, DC, and CEF, which can be performed with the same equipment. Additionally, the CEF instrument can perform temperature gradient interaction chromatography analysis simply by replacing the column with a graphitized carbon-1 and performing similar cooling and heating cycles, providing an extended separation of PE resins down to amorphous grades. The separation mechanism in TGIC analysis of PE copolymers results in a linear relationship between the number of branches and elution temperature, as it happens with crystallization techniques like TREF. TREF provides better resolution than TGIC in the analysis of industrial LLDPE resins covering the range of densities between 0.96 and 0.90. However, TGIC desorption temperatures are around 50 degrees Celsius higher than TREF's dissolution temperatures. Consequently, TGIC can separate amorphous resins without needing subambient conditions. Polypropylene resins, however, with so many branches in the linear chain, result in such low adsorption strength under cooling that crystallization forces appear before adsorption does. Isotactic PP elutes in TGIC at the TREF temperature. Meanwhile, PE desorbs at a much higher temperature. The elution temperature of polypropylene and polyethylene homopolymers is shown here for the crystallization and chromatographic techniques. The separation by TGIC of both homopolymers is superior to that of the crystallization techniques. The separation temperature range of all the propylene-ethylene copolymers is also shown, starting with isotactic PP and increasing the ethylene incorporation to the PE homopolymer. Polyolefin resins combining polypropylene and polyethylene fractions cannot be unequivocally identified solely by the elution temperature of any single technique, as there are two possible solutions. The simultaneous analysis of the methyl content by the IR6 infrared detector in the CEF instrument differentiates an ethylene-rich from a propylene-rich resin on all the techniques, as shown by the numbers at the crossing points. To further characterize an unknown resin, a full bivariate distribution, composition and molar mass dependence may be required. This is analyzed in a separate instrument that obtains the bivariate distribution by combining TREF or TGIC with GPC. Cross-fractionation chromatography, or CFC. A good example is the analysis of a high-impact polypropylene polymer by CFC in TREF mode. The various components in this resin are well distinguished: isotactic PP with a tail towards lower molar mass, the LLDPE produced at the time of obtaining the rubber fraction, with a distinct small polyethylene peak from the LLDPE linear fraction that, when doing the experiment in TGIC mode, is separated above the polypropylene peak. Over the past 30 years, Polymer Car has developed advanced crystallization techniques to create fully automated methods for polyolefin microstructure characterization, making them commercially available. The versatile CEF instrument performs the most essential crystallization techniques like CEF, TREF, DC, and additionally, TGIC by simply changing columns. The well-established Christoph technique is also available as an instrument. CFC can be performed in two modes: TREF GPC or TGIC GPC. Designed and developed by Polymer Car, your trusted partner with over 30 years of experience in advanced polyolefin characterization instrumentation and world-class analytical services.